Hi, everybody. Before I begin, I would like to make you a question. Have you ever thought about all the applications of ice? You're probably thinking that you can use ice to cool your beverage. That's a good and valid question. But if you're a scientist that knows about isotopic fractionation, you're probably thinking that you can use ice from ice bodies in order to depict planet Earth climate distribution throughout the millennium. So wait, what are isotopic fractionation maps? So this is my topic, and I'm Lozano Garcia, Eduardo Alejandro from Instituto Politécnico Nacional, and my BMSIS YSB mentor is Dr. Chris Butch from University of Nanjing, China. So first, what are isotopes? You can probably think of isotopes as different versions of an atom. For instance, here we have carbon 12, 13, and carbon 14, I mean. You can see that carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons, and carbon 14 has 6 protons and 8 neutrons. Extra neutrons will contribute to the mass of the atom. This will not affect the types of bonds it can form, but it will create different energy states. Thus, the thermodynamics will change. So this is an important aspect. Different mass equals different energy. You can think about bonds as rings. If you change the mass, the period is going to be different. And when you think about bonds in equilibrium with each other, you're thinking about isotopic fractionation. So isotopic fractionation is defined as a relative partitioning of the heavier and lighter isotopes between two coexisting phases in natural systems. Or in short words, you can think about isotopic fractionation of the distribution of isotope A to respect to a substance and the distribution of isotope B respect to a substance and so on. This might not probably that clear, so let's use an example. Here we have Legos, and let's compare main brand Legos and off-brand Legos. For instance, here we have a Lego structure that is supposed to be the same, but you can see that these two Lego pieces are different Legos. This is main brand, this off-brand. So the property of the stickiness of this off-brand Lego is gonna differ, and you see how it felt. So this is basically the idea that different isotopes give different properties, though with the same structure. And you know what? It's actually hot here in Mexicali. Here's the desert, so I'm thinking of going to the beach. So wait, how is the beach and the ocean related to isotopic fractionation? That's also a good question. So here we have the ocean, and we have water. Water is made of oxygen and hydrogen. We can have oxygen 16 and oxygen 18. So the energy of the sun is going to be able to evaporate this water. And we have two cases. In colder days, the energy is not going to be enough to evaporate heavier isotopes, meaning that oxygen 16 will be able to evaporate, then it will come back as precipitation, and hopefully we cross our fingers that lands in an ice body. Then in another case, when it's hotter, the energy is going to be enough to evaporate oxygen 18, or the heavier isotope. And we hope, again, that it lands on the same ice body. This will form a layer, and voila, we can use isotopic fractionation, or the distribution of these isotopes, in order to depict the climate of planet Earth. And I mean, this is not the only application of isotopic fractionation. For instance, you see carbon dioxide fractionation in different reservoirs, such as ocean, atmosphere, and soil, is used to evaluate a lot of stuff. For instance, here in soil, we see that the isotopic fractionation of carbon 13 is actually negative, meaning that might imply that biological systems tend to prefer carbon 12, and many more. We can use isotopic fractionation to predict the precipitation of a certain region throughout history. There's a really interesting paper published this year on April that talks about how they use isotopic fractionation to depict precipitation in Southeast Asia. So we've seen how important are isotopic fractionation of different atoms. So we now want a method in order to obtain these numbers. So throughout history, there have been numerous efforts to obtain this. For instance, we have empirical force fields for simple molecules. We have Galimov spawn additivity method, and the electronic structure method for large organic molecules. And I gotta say that all these methods are valid, but when we are talking about computational chemistry, we are worried about a method that is numerical stable and simple somehow because we want to be able to scale this. And before I go on with this, I want to point out this important idea in biology and computational biology that molecules are graphs. Here you have a molecule. You have atoms and bonds. But if you think about this, you can define this as a mathematical object called graphs that has nodes and edges. So that means that we can use molecules as graphs in order to implement graph algorithms. And when we're talking about graph algorithms, we know that a lot of computer science is about this. We see that we have to face big O complexity and time complexity, data structure optimization, scalability, and accuracy. These are really important points that if you want to discuss at the end, I will be happy to do it. So let's focus on Galley-Mills additivity method. Here we have a graph. We can subdivide this graph into two fragments. And we can subdivide those fragments into a subset of fragments that we can call, for instance, L factors. And if we sum up over all these L factors, we can obtain the contribution of all those factors to a specific atom. And with that, we can predict the isotopic fractionation of a specific atom and an entire isotopic fractionation of the molecule of all its atoms. So this was implemented in Python and ArcticKit. And here you have the algorithm. We were able to do this for a small data set so we could validate our algorithm. And here you have some of those molecules. You can see that we not only calculated the isotopic fractionation of these molecules, but we also created a map that has a visualization of the magnitude of different atoms. So far, we've been able to do this for carbon and nitrogen. But in the future, we want to do this for many other isotopes of different atoms. And so we made the code really easy to adapt to more atoms. And here we have another thing that we calculated with that data. So here is the cyanide polymerization network. In the y-axis, you have the isotopic fractionation. In the x-axis, you have the iteration. And in gray, you have isotopic fractionation of carbon. And in blue, you have isotopic fractionation of nitrogen. And we can see how this isotopic fractionation is evolving over iteration. This isotopic fractionation is unique to a network, so it can be used to identify a network. And it can also be used to identify origins of life and many more things. So here we have our algorithm versus the experimental data. In the y-axis, we have the deltas, and in the x-axis, we have atoms. So these are the atoms of all the molecules of our data set, the one that you saw previously. And for the most part, we can see that our predictions are accurately. But there was a point in which we got a huge error. And this is because isotopic fractionation, and specifically this method, relies on having the L contributions hard-coded. So this is a problem that we need to improve. So how to improve? Right now, we're working on that. We're working on machine learning, data augmentation, and data structures in order to improve this. So we want to learn L factors of atoms that we know of, but also of those atoms that we don't have much information, so that we can make accurate predictions of things that aren't that accurate right now. And before I end, I would like to thank all the collaborators. This is a really understatement because there were many people involved throughout continuous education. So I would like to say thanks to Dr. Boswell from University of Colorado, Dr. Sean from Tokyo Institute of Technology, Dr. Jim Reeve from University of Colorado, and special thanks to Dr. G. Day Scram from Stanford Graduate School of Business, and Dr. Graham from our Space Institute of Science for helping me improve the slides. And of course, to people from the Explainables NASA Ames, and all the people that help us throughout this program. And well, thank you for your attention. And are there any questions?
Thank you so much, Alejandro. Really interesting presentation. The floor is open for questions.
Good job, Alejandro.
Alejandro, is the additivity method you're talking about basically just a Benson's group additivity trick? Like you said, you consider the contribution of individual bonds?
Sorry, I was not able to hear clearly because of lag. Could you repeat that or either type that?
Yeah, I typed it. Can you scroll up?
Okay, yeah. Let me see. No. So actually, the isotopic fractionation method that we used is a method described by Galimov. Galimov has actually wrote a book about isotopic fractionation. It's a really interesting book. I could share that with you. And yeah, it's basically 400 pages of isotopes, isotopic fractionation, and the additivity method.
All right, so send me that over Slack, maybe.
Yeah, sure. I can share that in Slack. Are there any other questions?
If not, I have one. Alejandro, as you know, there's been this interesting discovery that on Mars there is methane, so CH4, that's been discovered. That is this big, I don't know how big it is, but it's this possibility that it's either produced geochemically or biologically. There are organisms that produce methane, and there are just chemical reactions with water and rock that produce methane as well. And from what you know about isotopic fractionation, could that be a technique to differentiate the two origins?
Yeah, so actually, I forgot to mention, we were working on this. So it's a open source tool. It's gonna be published in Python PyPL, so you can install it from in your Python package. So yeah, we were thinking to use this as a tool so you can do some analysis. Though the specifics of the interpretation, I'm not an expert on the subject, so that would depend on the person that used this data. So that's why we were giving a lot of freedom on how to use this tool. But for instance, I know of that there is a research group that is interested on using this tool in order to understand a simulation of primitive metabolic networks of Earth and understand the distribution of carbon.
Sorry, I'm not sure if you understood my question. My question was about methane on Mars and whether using isotopic fractionation, you could identify whether the origin is biological or geological. Yeah,
so as I said, like I don't have an expertise on this subject to answer your question clearly.
Okay,
that's why we enable our users to have power over how to use this tool and interpret the data. I'm sorry if I didn't answer your question.
Oh, that's fine. Any other questions from Alejandro?
Just to say congratulations, Alejandro.
Thank
This is
you.
Dr. Ernesto Duarte from CETIS University, down in Mexicali.
Thank you.
Your picture of the beach really makes me envious.
Yeah, that's better than the desert reality down in Mexicali.
Fantastic. Thank you very much, Alejandro. Nicely done.
Thanks to you.